What if the next revolution in computing isn't about building a faster computer, but about changing the very way reality is used to process information? That question has moved from science fiction into serious scientific discussion following Google's announcement of its latest quantum processor, known as Willow. While the headlines focused on incredible processing speeds, many researchers were interested in something far deeper. Not simply how fast the chip performed, but what its success tells us about the strange rules that govern the quantum world. Unlike the computers we use every day, a quantum computer doesn't solve problems by checking one possibility after another. Instead, it follows an entirely different set of physical principles. To understand why this matters, let's first look at how ordinary computers work. Every smartphone, laptop, and supercomputer stores information using bits. Each bit has only one possible value at any moment, either a 0 or a 1. No matter how powerful a classical computer becomes, it still processes information using enormous collections of these simple binary states. Quantum computers work differently. Instead of bits, they use qubits. A qubit can behave according to the rules of quantum mechanics, allowing it to exist in a combination of states until it is measured. This property, called superposition, allows quantum computers to represent many possible configurations during certain calculations. Another remarkable feature is entanglement. When qubits become entangled, the state of one qubit becomes linked to another, even though each qubit cannot be fully described on its own. These relationships allow quantum algorithms to solve certain specialized problems far more efficiently than today's classical computers. Maintaining those fragile quantum states is incredibly difficult. Even tiny vibrations, heat, or stray electromagnetic signals can disturb the calculation. That's why quantum processors operate inside highly controlled environments cooled to temperatures only a fraction of a degree above absolute zero. Creating those conditions is one of the greatest engineering challenges in modern science. Google's Willow processor represents another important step in overcoming these obstacles. During a specialized benchmark designed to test quantum performance, the processor completed a calculation that would be extraordinarily difficult for classical computers to reproduce using conventional methods. It's important to understand what that means. The benchmark was created to demonstrate quantum capabilities. It wasn't solving climate change, discovering new medicines, or searching for alien signals. Instead, it showed that quantum hardware continues to improve and can outperform classical systems on carefully chosen computational tasks. Even so, the result attracted worldwide attention. Not because it proved quantum computers could replace every existing machine overnight, but because it demonstrated how rapidly the field is advancing. As these systems become larger and more reliable, they may eventually help scientists simulate complex molecules, design advanced materials, improve cryptography, and solve optimization problems that challenge today's most powerful supercomputers. Still, quantum computing raises questions that extend far beyond engineering. Why does quantum mechanics allow these strange calculations in the first place? What is really happening while a quantum computer performs its work? Physicists have debated those questions for decades. One of the most famous ideas is known as the many worlds interpretation, first proposed by physicist Hugh Everett III. According to this interpretation, quantum events do not force reality into a single outcome. Instead, every possible result continues in its own branching history. It is a fascinating concept. But it is only one interpretation of quantum mechanics. Other interpretations explain the same mathematical predictions without requiring parallel universes. At present, no experiment has confirmed which interpretation, if any, represents reality. That distinction is extremely important. Google's Willow processor does not prove that parallel universes exist. It does not communicate with alternate realities. And it certainly does not open portals into other dimensions. Those ideas belong to speculation, not established science. What Willow does demonstrate is that quantum mechanics describes nature in ways that often defy our everyday intuition. The equations work remarkably well. Yet their deeper meaning remains one of the greatest mysteries in physics. As quantum computers continue to improve, they may not only transform technology. They may also help scientists ask entirely new questions about the fundamental nature of reality. And that possibility is where the story becomes even more fascinating. If Willow's greatest achievement wasn't simply speed, then what was it? The answer is something far less dramatic, but potentially far more important. Reliability. For years, quantum computing faced one enormous obstacle. Building a quantum processor with more qubits didn't automatically make it more powerful. In fact, it often made things worse. Quantum information is incredibly fragile. Even the smallest disturbance, a tiny vibration, a slight temperature change, or a stray electromagnetic signal, can introduce errors into a calculation. As engineers added more qubits, those errors multiplied. For a long time, this seemed like the biggest barrier preventing quantum computers from becoming practical machines. Google's Willow processor was designed to tackle exactly that challenge. Instead of focusing only on increasing processing power, researchers worked on reducing errors as the system became larger. This approach, known as quantum error correction, is considered one of the most important goals in quantum computing. If quantum information can be protected long enough, future quantum computers could perform calculations that are impossible for today's machines. That's why many scientists viewed Willow's results as a major engineering milestone. Not because it solved every problem, but because it showed meaningful progress toward building stable, scalable quantum computers. Still, the strange nature of quantum mechanics continues to inspire fascinating questions. How can particles behave in ways that seem completely different from anything we experience in everyday life? Why do mathematical equations describing quantum systems work so well while their deeper meaning remains uncertain? These questions have led physicists to propose several different interpretations. One of the best known is the many worlds interpretation. According to this idea, every possible outcome of a quantum event continues to exist in separate branches of reality. If that interpretation is correct, reality could be far more complex than our daily experience suggests. However, there is an important point that often gets lost in sensational headlines. There is currently no experimental evidence proving that quantum computers access parallel universes. Willow did not discover another Earth. It did not receive information from another dimension. And it did not create a doorway into the multiverse. Those claims are not supported by scientific evidence. What quantum computers actually do is use the well-tested principles of quantum mechanics, superposition, entanglement, and interference, to perform certain calculations in ways that classical computers cannot efficiently imitate. That alone is remarkable. Without invoking science fiction, quantum computing already represents one of the greatest technological achievements of the modern era. Its future applications could reshape many fields. Scientists hope quantum computers will one day accelerate the discovery of new medicines, improve climate modeling, design advanced materials, optimize transportation systems, and strengthen our understanding of chemistry and physics. Some experts believe these machines could revolutionize industries over the coming decades. Others caution that many technical challenges still remain before large-scale, fault-tolerant quantum computers become common. Either way, the direction is clear. Quantum computing is moving from laboratory experiments toward practical technology. And with every breakthrough, researchers gain a deeper understanding of one of nature's most mysterious sets of laws. Perhaps the biggest lesson from Willow isn't that we've uncovered all the answers. It's that we've discovered how much we still don't know. The quantum world continues to challenge our intuition. It reminds us that reality operates according to rules far stranger than anyone imagined a century ago. Whether those rules eventually reveal new physics, or simply deepen our understanding of existing theories, one thing is certain. The next generation of discoveries won't come from asking whether quantum computers are magical. They'll come from understanding how nature itself performs calculations at its most fundamental level. And somewhere inside that invisible quantum world, the future of computing may already be taking shape.